this video, we are going to be looking at a JC1 promotional exam paper from Univer Junior College in the year 2020. So the first question that we have here is a system of linear equation question where we are supposed to solve for the total number of cupcakes bought by Amy, Bobby, and Carla. So the first thing that I'm going to try to do is to define the variables, and I'm going to go for the number of cupcakes bought by Amy to be A, the number of cupcakes bought by Bobby, I'll go for B, and the number of cupcakes bought by Carla, I'm going to go for C. And the question says that Amy bought 4 cupcakes fewer than Bobby and Carla combined. So A is going to be equal to B plus C. It is going to be 4 more, so minus 4. This gives me my first equation, which is going to be A minus B minus C. This is -4. This will be my first equation. And then Amy paid $14 more than Bobby and Carla combined. So this, since Amy, according to what the question says, Amy paid $5 for each of her cupcakes. So 5A is going to be the total amount that Amy has paid. And this is $14 more than the total amount of money that Bobby and Carla has paid. So for Bobby, it is going to be $4 per cupcake. So it's going to be 4B. And for Carla, it's going to be $3 per cupcake. So it's going to be plus 3C. And this is going to be less than, or rather for Amy, she's paying more than these two combined. So this plus $14 more, this will form for me my second equation. So from here, we will have a 5A minus 4B minus 3C. This is equal to 14. This is equation number 2. And if Amy and Bobby paid $3 each for their cupcake, so for Amy, $3 each for the cupcake is going to be 3A, and for Bobby, $3 each is going to be 3B, and this amount is going to be $14 less than what they would have paid. So this is going to be the original amount that they would have paid is going to be equal to $5 per, so 5A, $4 per, so 4B, and we minus 46, and this will be what the question is describing. This will give us our third equation, which is going to be, let me shift everything over to the right-hand side. So 5A minus this is going to be 2A, 4B minus this is going to be plus B. This is negative 46. I'm going to shift it over to the other side. This is going to be equal to 46. This will form for me the third equation. Pressing all this into the graphing calculator to let the calculator solve this system of linear equation for me, we are going to be getting A to be equal to 18. We are getting B to be equal to 10, and C will be equal to 12. So the total number of cupcakes that are bought by these 3 people will be 18 plus 10 plus 12, 40 cupcakes altogether. Let's move on to look at question number 2. So in question number 2, it is an inequalities question. We are given this part 1. We are supposed to solve this inequality. So this is an x squared minus x minus 1 divided by x plus 1. This is less than or equal to 1. And according to the question, we are just supposed to solve this inequality, but the question mentioned that we are supposed to solve it exactly, which is a hint that we should try to solve this algebraically instead of using the graph, just in case graph gives me solutions that is going to be not in this exact form. So let's try to solve this algebraically first. I'm going to bring 1 over to the left-hand side. So we have x squared minus x minus 1 divided by x plus 1 minus 1. This is less than or equal to 0. Let's combine this into one single expression. X squared minus x minus 1 minus x plus 1 divided by x plus 1. This is less than or equal to 0. So we will have an x squared, negative x, negative 2x. Then negative 1, this is going to give me a negative 2. This divided by x plus 1. This is less than or equal to 0. We're going to try to factorize the numerator further, but we are not going to be getting nice numbers. So we can't do the cross method to factorize this. That's why we are not expecting like the nice kind of numbers. And what I think I'm going to try to do is to either make use of the quadratic formula to find the roots of the numerator, or for me, I think actually personally I would prefer using completing square to form for myself a square minus b square scenario. Then I'll factorize it further. So let me complete the square for this. It is going to be x minus 1 square minus 1 square minus 2. This is going to be minus 3 divided by x plus 1. This is less than or equal to 0. As for 3, I'm going to see it as if it is a square root of 3 square, so that I can have a square minus b square scenario. And this will give me a, factorizing this further, this minus square root of 3. And we have this plus square root of 3. This divided by x plus 1. This is less than or equal to 0. So from what we have here, and it's not very necessary to do this, but just for our presentation's sake, let's try to rewrite this into x minus its roots. So this is going to be this minus 1 plus square root of 3. Then x minus 1 minus square root of 3 divided by this, we will have x minus minus 1. Okay, this is less than or equal to 0. So this is just making it clearer for us to be doing it together. But of course, you don't really need to write down this step. Then I can draw my number line with 3 numbers. The smallest number would be this, -1. Then after that, it will follow by this. It's going to be 1 minus square root of 3. Then after that, the largest number, 1 plus square root of 3. So if I were to substitute a number that is bigger than 1 plus square root of 3 into this entire expression, the number should give me a positive number. I'm going to write positive here. If I were to substitute a number that is in between, an x that is in between here and here into this entire expression, I'm going to get a negative. If I were to continue to do that for this interval and then this interval, I'm going to get a positive and negative. And what the question wants is for something to be less than or equal to 0. So it's going to be this region here and this region here, which means that for what I have here, my solution is supposed to be x to be less than or equal to -1, or x is supposed to be bigger or equal to 1 minus square root of 3, less than or equal to 1 plus square root of 3. But if I were to refer back to my original inequality, looking at the original inequality, I do want to acknowledge that if x is equal to -1, it's going to cause the denominator to be equal to 0, and it is going to cause the left-hand side to be undefined. So I have to reject the equal to. So my final answer for part 1 is going to be this set of values. Let's move on. Part 2. So for part 2, hence the question says, by making use of this, we are supposed to solve another inequality. Let's take a look at this other inequality, which we are suspecting there's going to be some similarity between this new inequality and the one that is given to us. And we are supposed to try to find that similarity. And most likely, we are going to be replacing all this x by another expression that is meant to solve for part 2. So for part 2, the inequality that is given to us is x squared plus x minus 1 over 1 minus x. This is less than or equal to 1. And we have been using a very interesting strategy that I try to showcase in different videos that talks about inequality, talks about us trying to replace x by another expression. And that is when I'm looking at this particular inequality that is going to be referenced to the previous one, of course, the best scenario is for us to be able to immediately recognize what x is going to be replaced with. But at the same time, we do want to know that if x is going to be replaced, that means the terms that are independent of x will not be replaced. So instead of focusing on the terms that x are going to be replaced, maybe let's try to focus on the terms that x are not going to be replaced first. For example, 1 is still going to be equal to 1. So this 1, I'm going to leave it as it is. -1 is not going to be replaced, so -1 is going to be here. And +1 is not going to be replaced. So for this that is in the denominator, let me just try to do a little bit of tweak by rewriting this as -x plus 1. This is less than or equal to 1. And I think just by doing this small little tweak, it makes it easier for us to try guess what x is going to be replaced with. So -1 plus 1 plus 1 minus 1 plus 1 plus 1 is setting the correct kind of condition for me to make a guess. My guess is x is probably going to be replaced by -x. So let's see whether this is going to be so if we can just try to see how much more we can manipulate this. For example, x squared, I can rewrite it as -x squared. then it will in a way match to this, where x is going to be replaced by negative x. How about plus x? Plus x, I can rewrite it as negative of negative x. Then minus 1 divided by negative x. Then plus 1, this is less or equal to 1. And they totally synchronize. It is just that x is going to be replaced by negative x. That is why for my answer for this, I'm going to replace all this x by negative x. So negative x is supposed to be strictly less than minus 1, or negative x is going to be bigger or equal to 1 minus square root of 3, less or equal to 1 plus square root of 3. Multiplying negative throughout, this will give me x to be bigger than 1. Multiplying by negative throughout, this will give me x to be bigger or equal to negative 1 negative square root of 3. This will become negative 1 plus square root of 3. So this is for part 2. Let's take a look at part 3. Okay, it is not part 3, it is question number 3. So in question number 3, the very first thing that we should try to do is to try to sketch the graph of this. So for this, we have a graph of rational expression to sketch. It is an improper rational expression. We're given this. Y is equal to x squared plus 9x minus 5 divided by x plus 10. And in order for us to sketch this graph, and we are actually already expecting that this graph will have an oblique asymptote. I think the vertical asymptote is pretty obvious. It is when x is equal to negative 10. But for the oblique asymptote, we do need to do a long division. Let's try that. So to do a long division to this, we have x squared minus 9x minus 5. This is going to be divided by x plus 10. So here will be x. Then we have x squared. Then it is going to be plus 10x. So minus, I will have a negative x, negative 5. Here I will go for negative 1, which will give me a negative x, negative 10 minus minus. This is going to give me a 5. So what we have here is going to be a x minus 1 plus 5 over x plus 10. That is obtained through the long division. So based on this, now we can know that the graph is going to be having a vertical asymptote of x is equal to negative 10, and you have an oblique asymptote of y is equal to x minus 1. Let's sketch in the asymptotes first. Then after that, we will make use of our graphing calculator to give us a hint of how the shape is going to be like. Then I'm going to sketch in the rest of the parts of the graph. So vertical line here is going to be representing the y-axis. Then I'm going to have a horizontal line. I'm going to draw it here. This will be representing the x-axis. We will have an oblique asymptote, which is this. It has a positive gradient, and it's going to be passing through the point 0, minus 1. So I'm going to draw my oblique asymptote here. Okay, we will use dotted lines to represent reference lines. This is y is equal to x minus 1. We do need to make sure that we indicate the oblique asymptote. There's a vertical asymptote. It is the value of x that caused the denominator here to be 0. Is the value of x that caused y to be undefined. That is at negative 10. So let me draw it here. Okay, a vertical line. This vertical line, I will call this x is equal to negative 10. From the graphing calculator, we can see that there's going to be a turning point here, and I'll make sure that my graph is tending towards the asymptote. So we have this, and as for this part here from my graphing calculator, we also have our coordinates. It is going to, we also have our graph. The graph is going to be like this. Here, it is going to have a turning point here, and it's going to curve back up. This is my graph, and we should try to indicate all the points where the graph makes turning point, which is this point, this point. We should also try to indicate all the xy intercept, and there's going to be 1 here and 1 here. So for this point here, this point here, okay, let me just indicate it here. Okay, for this point here, it is equal to, the coordinates is equal to negative 9.52 and 0. And for this point here, it has a coordinates of, this point here is 0.525, and a 0. And as for this over here is going to be a 0 and negative 0.5. And we have a minimum point here. Using the graphing calculator, this minimum point here is going to be at negative 7.76 and negative 6.53. And finally, we have a maximum point here. And for this maximum point, it has a coordinates of negative 12.2 and negative 15.5. Okay, so these are the coordinates and the asymptotes that define the graph. And okay, let me just indicate the equation of the graph. This is the graph of y is equal to x squared plus 9x minus 5 divided by x plus 10. Okay, this is for part 1. And then in part 2, the question says, hence, we are supposed to find the range of values of k, where k is a real number, such that this equation here, let me quote the equation, this x squared plus 9x minus 5 over x plus 10, which looks exactly the same as this. This is equal to kx plus 10k minus 11. And this equation here is supposed to have no solution. And we want to try to give a reason why, what is the range of values of k, why there is no solution. Okay, why that range of values of k is going to result in this equation here being having no solution. So this is a simultaneous equation question. So it is when I combine an equation, this y is equal to this, with another equation simultaneously. So the other equation is going to be this, y is equal to kx plus 10k minus 11. But because we are trying to be using our graph to discuss about the simultaneous equation, so this is going to form for me my second graph. So to work on this, trying to discuss its solution based on k, I'm going to try to sketch in my second graph. And I have a problem because for my second graph, although I can recognize that it is a straight line, but we can't really sketch it here, right? Because I don't know what is k yet. So if you're to try to observe from this equation here, this line equation, although we cannot draw the full line, but there are points on the line that I do know how to draw, right? If you were to look at this, are you able to see that if I were to let x here be equal to negative 10, so if x is equal to negative 10, what we will be getting, y is going to be equal to k times of negative 10 plus 10 times of k minus 11. Y is going to be equal to negative 11, which means that this line here will be passing through the point negative 10 and negative 11. It is a point that is independent of k, which means that although I can't draw the entire line, but I can draw a point that is on the line, and that is negative 10, negative 11. Let's try to find this point on our graph. X is equal to negative 10. It must be a point that is here. And usually from experience, the point that is going to be here, right, is going to be a prominent enough point. So if you were to just look at this, there are two prominent enough points. One is here, the other one is here. I don't think there's much that I can make use of for a point that is here. The y coordinate is 0. How about the y coordinate that is here? When x is equal to negative 10, negative 10 minus 1 is negative 11. So this point here is actually the point negative 10, negative 11, the point that this line is going to be passing through. And in order for this equation here to have no solution, what we need to do is to make sure that this line will not cut the graph at all, right? So can we try to draw a few lines to see how this line can be positioned here such that it passes through the point negative 10, negative 11, and it will not cut the graph at all. So if I were to draw it this way, obviously the line is going to be cutting the graph, right? So we can draw it this way, and it is not going to be cutting the graph. We can even draw it this way with a negative gradient, and it will still not be cutting the graph. In fact, I can even draw it to be a line that is here, exactly synchronizing to the oblique asymptote, and it will still not cut the graph. So based on this, I think this is the line that is going to give us insight into how we are going to be defining k, because we can see that whether it is this line, or this line, by pivoting at this point negative 10, negative 11, the thing that is changing is the gradient of the line, and the gradient is k. So the maximum possible the gradient can go is going to be when the gradient is 1, synchronizing to this oblique asymptote, that will be when k is equal to 1, because k is representing the gradient. So k is equal to 1, k is going to be less than 1, k is still going to be less than 1, negative is still going to be less than 1, all the way until when it is like here, which is going to be going towards negative infinity. All this will make sure that I'll be getting a line that is not going to be cutting the graph. Therefore, based on this reasoning, I can say that k must be one that is less than or equal to 1. So this is going to give me my answer for part 2. Let's move on. Let's take a look at question number, the next one, question number 4. So in question number 4, we have this. Let's take a look at it. Okay, in question number 4, without using a calculator, we want to show that the curve that is defined parametrically by that is going to be intersecting the line y is equal to x at 2 distinct points. So we have this, the parametric equation, x is equal to t squared plus t, and we have y is equal to t cubed plus t squared. This is for the curve, so these two equations will function at the same time. They will be functioning, at the same time. So, and we have another line. This line is the line y is equal to x. So we have a curve, we have a line, and we are going to be trying to discuss about the intersection between this curve and this line. So what we're going to do is to solve simultaneous equation. So we want to check that the solution to the simultaneous equation is going to be at only 2 distinct set of solution, which will then tell us that the curve and the line y is equal to x is going to be cutting at only 2 distinct points. Let's see whether we can see this happening. So I'm going to call this equation number 1 and 2, although they are actually belonging to the same curve, and I'm going to call this equation number 3. So to solve for the intersection, I'm going to just try to find something in common between the curve and the line. And to do that, I am going to first find t. Okay, so I'm going to substitute equation number 1 and equation number 2 into equation number 3. So on the left-hand side, it's going to be y. So we have a t to the power of 3 plus t squared. On the right-hand side, we have x, which is going to be t squared plus t. So shifting everything over to the left-hand side, we have a t to the power of 3 minus t, this is equal to 0. Factorizing this, we have, we can only factorize out t. So factorizing this, we have a t, then there's a t squared minus 1, this is equal to 0. T is going to be equal to 0, or t is going to be equal to plus or minus. Okay, we have 3 t's. No wonder the question wants us to try to show that this curve has 2 distinct points, because now we have 3. 3 t's is going to be giving us 3 points, but we are expecting that of these 3 points, 2 of them are probably the same. So if we can somehow show this, then we will have 2 distinct points of intersection. So let's try to check that by going through these 3 different values of t one by one. So when t is equal to 0, let's try. When t is equal to 0, then x is equal to 0 and y is equal to 0. So we have a point 0, 0. And when t is equal to, let's see, when t is equal to negative 1 from here. When t is equal to negative 1, x is going to be equal to negative 1 square, then negative 1. This is going to be 0. And y is going to be negative 1 to the power of 3 plus negative 1 square. This is going to be also, this is actually also going to be equal to 0. So we have another point, 0, 0, that is formed when t is equal to negative 1. And these 2 points, they're actually the same. Okay, so they are not considered a distinct point. Let's hope that this is going to be distinct. When t is equal to 1, x is equal to 1 square plus 1. This is equal to 2. And y is going to be 1 to the power 3 plus 1 square. This is also going to be equal to 2. So we have one more point, and that point is 2, 2. Therefore, we have 2 distinct points. And the 2 distinct points, therefore, we have 2 distinct points, and the 2 distinct points are 0, 0, and the other one is 2, 2. Okay, which is what the question wants us to prove. Next, prove that this line is normal to the curve at exactly one of these points, at exactly one of the points. Okay, it is going to be normal at exactly one of the points. Okay, but let's take note. Okay, for this 0, 0, it is going to be from 2 possible t's. So, okay, the question says that the line must be normal. Prove that this line is normal to the curve at exactly one of the points. So this line, let me just draw, okay? This line must be normal to the curve. This line that we are talking about is the line y is equal to x. And this is normal to the curve. So we have something that is like this. Normal to the curve means that this line is going to be perpendicular to the tangent. Okay, which means that we are expecting that the gradient here, the gradient of the curve here is, what is dy dx? We're expecting the dy dx to be equal to -1 over this, because the gradient of this line is 1. So we're expecting this to be equal to -1. So let's try to check whether there's only exactly one point of these 2 points, okay? Exactly one of them is going to be giving us a normal that is going to be this y is equal to x. So we're going to check by making use of gradient. Okay, we're going to see which point is going to give us a gradient of -1, and that is going to be the point where this is going to be. Okay, where the normal is going to be this y is equal to x. So to do that, let's get an expression for dy dx. So to get dy dx, we will first need to find dx dt. Dx dt is going to be equal to 2t plus 1. And we will also need dy dt. dy dt is 3t squared plus 2t, which means that dy dx, which is equal to dy dt divided by dx dt, is going to be 3t squared plus 2t over 2t plus 1. Okay, now let's go through the 3 different values of t one by one. When t is equal to 0, okay, we want to see for ourselves, okay, with numbers, that only one of the dy dx is equal to -1. Then we will be able to prove what the question wants us to prove. So when t is equal to 0, okay, at the point 0, 0, when t is equal to 0, we know that when t equals 0, this is going to be at the point 0, 0. dy dx, let's check. Dy dx here is going to be when t is good. Oh, dy dx is just going to be equal to 0. I'm not getting a -1. So this is not the point. Let me just mark across myself. Okay, so this is not. And let's see what is going to happen when t is equal to -1. And when t is equal to -1, we are again at the point 0, 0. Let's see whether we are actually still going to be getting the same gradient as 0, or will we get this? Okay, they are the same points, but we may be getting different gradients. Okay, let's see whether this is possible. So dy dx here, this is equal to dy dx here. Okay, I'm going to substitute -1 into this. So it's going to be 3 times of -1 squared plus 2 times of -1 divided by 2 of -1 plus 1. And this is actually going to be giving us, when t is equal to this is going to be giving us a -1. It is what we are trying to find. So this is when the normal to this point is actually this line, y is equal to x. Let us check one more, because we are supposed to prove that there's only one. Okay, if I cannot prove, I mean, if this turns out to be -1, then we didn't manage to prove it. So when t is equal to 1, and this is at the point 2, 2. When this happens, dy dx is going to be equal to, substituting into here, it's going to be 3 times of 1 squared plus 2 times of 1 divided by 2 times of 1 plus 1. And this is equal to 5 over 3. So this is not equal to -1 that we are trying to find. This is also not equal to -1 that we are supposed to find. So the only point that is going to be giving us a normal to the curve that is going to be y is equal to x is going to be this one. Okay, only one of them, which prove what the question wants us to prove. But just to elaborate on this question a little bit more, right? Is it actually possible for something that is like this to happen? Because we have one single point, but we have 2 gradients. Yes, it is possible if you were to just try to plot out this graph on your graphing calculator. You realize that this graph looks something like this. Let me just very quickly show you. Okay, this graph looks something like this. Here. Okay, so we have it as something like this. Here, Okay, at a point 0, 0, it will curve this way. Then after that, it's going to curve back down and do a loop here and going back up here like this. This is going to be the graph when I try to plot this curve. Okay, and if you were to look at the point 0, 0, there are actually two gradients, two tangents, right? At the point 0, 0 here, based on this part of the graph, based on this part, the tangent is going to be this, which means that the normal, which is 90 degrees to the tangent, is this y is equal to x. So at the point 0, 0, we see a normal that is going to be the line y is equal to x. And at the same time, at the point 0, 0, we are seeing another behavior that is happening. This is when the tangent is parallel to the x-axis because dy dx is equal to 0. And that happens for this part of the graph. For this part of the graph, the tangent is actually this. Okay, this is when dy dx is equal to 0 at a point 0, 0. And its normal is going to be this vertical line, x is equal to 0. Okay, that is why we are seeing two different tangents at the same point. Okay, if you have to draw the graph, you should be able to see this. Anyway, this is question number 4, which they didn't ask us to explain that much. We are just elaborating a little bit since we are seeing a strange little behavior that is happening here. It is not going to affect our solution anyway. So let's move on. Let's take a look at question number 5. Question number 5, we have it in 2 pages. So let me just display it this way, okay? Okay, question number 5, it is a vectors question. Part A, we are given 2 pieces of information. The first one is this u dot 4, 1 minus 2. This is equal to -6. The second piece of information, sorry, u is a vector. So the second piece of information, u cross 1, 2, 3. This is equal to k times of 1 minus 2, 1. I mean, cross product, it is a vector. Okay, so we are seeing that this vector here is k times of this. So this actually indicates to me that u cross 1, 2, 3 is parallel to vector 1 minus 2, 1. Okay, so we are looking at the information that is like this, and based on this, we want to explain why u dot 1, -2, 1 is equal to 0. U dot 1, -2, 1 is equal to 0. So it is trying to ask us to explain why is it that vector u is perpendicular to 1, -2, 1. It is actually pretty obvious because u cross this. Okay, if I were to look at it based on the 2 vectors that are lying parallel to a plane, and assuming that just for the ease of us visualizing, let's assume that they are on the same plane. Okay, so they need not be on the same plane, but assuming they are on the same plane so that it's easier for us to visualize, we are seeing, for example, vector u that is here, and the other vector is this vector 1, 2, 3. So when I do a cross product, it is going to give me something that is like this, right? U cross this vector. So u cross this vector, 90 degrees to this, 90 degrees to this. It is going to give me a u cross 1, 2, 3. And what the question says is that this 1, -2, 1 is parallel to u cross 1, 2, 3, which means that this, let me just draw it here, let's say. Okay, so this vector, which is parallel to this is going to be 1, -2, 1. So we know that u is going to be perpendicular to this, and this is parallel to this. That is why when I take u dot this vector, u dot 1, -2, 1, where these are also going to be perpendicular to each other, will be equal to 0. So based on this, it is going to be what we're going to be describing in our solution. So this is meant for part 1. Next, we want to try to find a set of values of vector u to describe this set geometrically. So u satisfy this, u satisfy this, and u satisfy this. Okay, now we have the third piece of information. From this, it is extended to this. And we are supposed to try to geometrically define u. Oh, there's one more piece of information that is actually given to us. It is given to us that u changes. U is a variable vector. Okay, so u changes. So what I'm going to do is I am going to, in part 2 over here, right? Part 2 of part A, I'm going to let this u, since it's a variable vector, be x, y, z. So if I were to let u be equal to x, y, z, based on this piece of information that is given to me, x, y, z, u dot 4, 1 minus 2. This is equal to -6, which means that 4x plus y minus 2z, this is -6. And based on either this or this, I think I'm going to use this. Because if I were to use this, I'll have another k to try to resolve. So this is just one single unknown, which is u, which means that based on this, replacing u by x, y, z, this dot 1, -2, 1, this is equal to 0. So we have a x minus 2y plus z is equal to 0. And guess what? We have actually a pair of equation that is in terms of x, y, z. So with this pair of equation, I can then press it into my graphing calculator. And my graphing calculator will be giving me this. Let me just write down for you. From the calculator, I'm going to be getting x to be equal to -4 over 3 plus 1 over 3 z. Y is equal to -2 over 3 plus 2 over 3 z. And my calculator will tell me that z is equal to z. And seeing u as a variable vector, so now u, x, y, z, x, y, z, can be, if I were to rewrite this into its column vector form, can also be written as -4 over 3, then -2 over 3, and 0, then plus, here I'm going to go for a 1 over 3 times z, 2 over 3 multiplied by z, and z, which I can also rewrite this as -4 over 3, -2 over 3, 0, plus, let me just simply factorize out 1 over 3z, which will then give me from here, which will then give me a 1, then this is going to be equal to 2, then this is going to give me a 3. So this u here, which is a variable vector, is going to be equal to -4 over 3, -2 over 3, 0, then plus, I'm going to just call this 1 over 3z as lambda, okay? So it's going to be lambda of 1, 2, 3, and now we have an equation, a familiar equation. What is this equation? It is an equation that represents a line, correct? An equation of a line. So we can then say geometrically, u is going to be a line that passes through the point -4 over 3, -2 over 3, and 0. And this line is going to be parallel to a vector. The vector is going to be 1, 2, 3. Next, let's take a look at B. Okay, B, we have this. In part B, we are supposed to try to prove that A, B, C, they are collinear when I am given this piece of information, which is C is equal to lambda A plus 1 minus lambda B, where this A, B, C, they are position vectors of points A, B, C respectively. What I'm going to do is I'm going to try to regroup this a little bit, okay? So C here is going to be equal to lambda A plus B minus away lambda B. If I were to shift this over to the left-hand side, we have a C minus B. This is going to be equal to lambda. Grouping this together, we have a minus B. So C minus B is the vector B, C. And A minus B is the vector B, A. So we have BC is equal to lambda of BA. For example, BC, point B, point C is lambda of BA, BA. So let's say it's going to be this. So let's say this is BC, let's say this is BA. And what this statement means is that they are parallel to each other, which is what I'm going to draw here. And since B is a common point, so the only way for us to physically draw BA and BC such that B is a common point and they are parallel to each other is for a scenario that is like this, right? B must be here, C must be here, and it's a common point. It must be parallel to BA. And therefore, based on this, we can then say that A, B, C, they are collinear. Okay, this is for part B. Let's take a look at part C. For part C, the question told us that there is this point P and it has a position vector P. So we know that OP is going to be this P. Oops, I was almost going to write a unit vector, but the question didn't say that it's a unit vector. It is a non-zero position vector P. And we have this plane pi. This plane pi is given to us as r dot n is equal to 0, where n here is a unit vector. That's what the question says. Okay, n here is a unit vector. So we know that for this, modulus of n is equal to 1. And I do want to highlight the fact that the other side of the equation in my plane equation is 0. What does this 0 imply? If it is any other values, maybe it is harder for us to think about the plane based on those values. But if this is 0, it just simply means that this plane passes through the origin, right? Because if I were to let r be 0, 0, 0 dot n, it is going to be equal to 0. So 0, 0, 0 satisfies this equation, which means that the plane passes through the origin. And if I were to just draw this plane pi, which passes through the origin O, and if point P is, let's say, here, that means OP is going to be this. And since the question says that n here is a unit vector, and we are supposed to try to find out what is the modulus of P dot n. And since n here is a unit vector, modulus of P dot n is the length of projection of P onto n. Okay, that's what we have learned using the length of projection formula. Okay, so if n happen to be a unit vector, according to what we have learned in our school's notes or on the Achevas TV outline, P dot n is the length of projection of P onto the normal. So the normal can be something that is like this. The length of projection of P onto the normal. So this portion here is actually modulus of P dot n. So what the question wants to ask, which is actually what we have just mentioned, what is the geometrical meaning of modulus of P dot n? Okay, so it is the length of projection of P onto the normal vector. Okay, that can be one of the answer. Or if you want to be even more specific, customizing it for this scenario, you can also say that P dot n is the shortest possible distance from the point P to the plane pi. Let's move on. Let's take a look at question number 6. For question number 6, A and B, they are integration question. So integration techniques question, we have this minus 5 minus 2x divided by this, which is square root of 7 minus 6x minus x squared. I'm going to try to check whether fx f prime x is going to work for this. So if I were to let fx be equal to 7 minus 6x minus x squared, then f prime x is equal to negative 6 minus 2x. Do we have a negative 6 minus 2x in the numerator? No, we don't, but we can create that. So I'm going to try to re-express this as minus 5. We need a negative 6. So I'm going to do a plus 6 so that I can have a negative 6, negative 2x. Okay, so that is what I'm creating here, divided by square root of 7 minus 6x minus x squared, which now I can rewrite this as this is going to be equal to 1. Then plus negative 6, negative 2x divided by this, which is square root of 7 minus 6x minus x squared. And I'm going to break this up into two different integrals. The first one will be 1 divided by this. 1 divided by square root of 7 negative 6x negative x squared. The other one is going to be this, obviously. So it's going to be plus negative 6 negative 2x divided by square root of 7 minus 6x minus x squared. As for integration of this, I think we need to tweak the denominator, especially the expression that is within the square root. I'm going to try to do a completed square form to this. So the completed square form of this is going to be square root of, this is going to be equal to 16 minus x plus 3 squared. If I were to do a completing square, and look at this 16 here, I'm going to re-express it as 4 squared. Okay, so we will have this. And plus, as for this, I'm also going to just try to tweak this a little bit. I'm going to write this as this, multiply by, instead of divide, multiply by 7 minus 6x minus x squared to the power of negative 1 over 2. So for what I have here, this can now be integrated because what we have is fx to be x plus 3 and f prime x is equal to 1, which is always going to be in front. So by making use of the formula that we have in our formula sheet, or if you have already memorized this, this is going to be related to sine inverse. So this is going to be sine inverse of x plus 3 over 4. Then as for this, integrating this is fx, this is f prime x. Okay, according to what we have discussed previously. So this is going to be 7 minus 6x minus x squared to the power of minus half plus 1 is going to be equal to half, then divided by half, then plus c. So my final answer for this is going to be sine inverse of x plus 3 over 4 plus 2 times of square root of 7 minus 6x minus x squared, then plus c. Let's take a look at b. For b, we are supposed to integrate this. Integration of 2 sine kx sine x dx. And in order for us to integrate this, I think one good strategy is to try to apply trigonometric identity. And I'm going to make use of the identity that is inside our formula sheet. So from my formula sheet, the MM26, this formula sheet, let's try to look for the trigonometric identity portion. And I think the one that is going to be suitable for us with a sine and sine is going to be this last one over here. Let me quote this. So from our formula sheet, we are seeing a cosine p minus cosine q is negative 2 sine of half p plus q sine of half p minus q. And our intention is to try to re-express this, which means that we're going to be making use of the right-hand side where we have a 2 sine sine. Okay, and if I were to see this angle here as A, and if I were to see this angle here as B, then the right-hand side can be converted to negative 2 sine A sine B. So how do I get P? P is obtained by taking A plus B. Because this plus this is going to give me a half p plus half p, which is going to be p half q minus half q, which will disappear. So this can be rewritten as a plus b. Similarly, if I were to take a minus b, half p minus half p will disappear. Half q minus half q will be half q plus half q. It is going to be q, which means that this q can be obtained by doing a minus b. So based on what we have in our MF26, in our formula sheet, we now customize another version that can help me to make use of this better by going from the right-hand side to the left-hand side and applying to this. Let me get back to the question. So from this, we are going to now rewrite. We need a negative, so negative 2 sine kx, then sine x dx. Re-expressing it using this, it is going to be negative integration of cosine a plus b. So cosine ax plus x. Then minus cosine a minus b, kx minus x. Okay, so we have this with us, and we are going to try to re-express it, okay? We are going to try to re-express this a little bit more first. So if I were to bring the negative in, then I can write this as the first term. Let me just bring the negative in, okay? So this will become cosine of k minus 1x, correct? Then negative times this is going to be minus cosine of, this will be k plus 1x. Then this dx, and now we are ready to do our integration. Integrating this gives us a sine of k minus 1x divided by k minus 1. As for this, it's going to give me a sine of k plus 1x divided by the coefficient, which is k plus 1, then plus c. Oh, we are done with part B. Let's move on to another one. Let's take a look at question number 7. In question number 7, we have this curve C. This curve C is defined for us as tangent inverse y is equal to x ln x squared minus 2x minus y. And in part 1, we are supposed to show that equation with dy dx. So we're going to be differentiating this. But before that, I think what we can try do is, let me just try to manipulate this a little bit by bringing down the 2. Okay, so it's going to be 2x ln x minus 2x minus y. So differentiating this with respect to x. On the left-hand side, I'm going to be getting a 1 over 1 plus y square. Implicit differentiation, so it is going to be this. On the right-hand side, I'm going to apply the product rule here. So it's going to be 2x, 1 over x, plus differentiating 2x is going to give me a 2. Then the other expression is going to be ln x, minus differentiating this is 2, differentiating this is minus dy dx. So we have a 2 minus 2. Then we will have a 1 over 1 plus y square dy dx. This will disappear, so this is going to be equal to 2 ln x minus dy dx. According to what the question wants me to prove, I shouldn't be having a 1 plus y square in the denominator as a coefficient here. So let me multiply this throughout by 1 plus y square. So we have a dy dx is going to be equal to 2 times of 1 plus y square ln x minus 1 plus y square dy dx, which I'm going to be bringing this over to the left-hand side. So we will have a dy dx plus 1 y square dy dx is equal to 2 1 plus y square ln x. And combining these together, we will be getting this 2 plus y square dy dx is equal to 2 1 plus y square ln x. Okay, this is what the question wants us to show. And next, we are supposed to find the coordinates of the stationary point. So stationary point, that is when dy dx is equal to 0, correct? So for part 2, we are going to let dy dx be equal to 0. So from this equation here, this is equal to 0, which means that we have a 0 is equal to 2 1 plus y square ln x. And 1 plus y square by itself, it cannot be equal to 0. So it leaves me with just ln x to be equal to 0. This tells me that x must be equal to 1. So we have the x coordinate. We are supposed to find the coordinates of the stationary point. This is not enough. We still need to find y. So when dy dx is equal to 0, x is equal to 1. To find the corresponding y, we're going to make use of the original equation here. So when x is equal to 1, based on the original equation, we will have a tangent inverse y is going to be equal to 1 time of ln 1 square minus 2 times of 1 minus y. So we have a tangent inverse of y. Then this, bring it over to the left-hand side, plus 2. This is 0. Okay, so we only have this. So bringing this over to the left-hand side, we have a plus 2 plus y. This is equal to 0. And to solve this, we are going to just try to sketch this on the graphing calculator to solve for the unknown y. So based on the calculator, okay, solving using the calculator from my graphing calculator, I'm going to be getting y as negative 1.4647. So therefore, stationary point is going to be at the point 1 and negative 1.4647. So, okay, this is part, which part is this? This is part 2. And by differentiating the result again, okay, part 1's result, we want to determine the nature of stationary point. So what this question wants is to make use of the second derivative to prove the nature of the stationary point. So I'm going to differentiate this again, okay, to get a d square y dx square. So differentiating this one more time, okay? So for this, I'm going to apply the product rule. So this d square y dx square plus is going to be 2y dy dx multiplied by dy dx again. Okay, so we have this. Then this is going to be equal to 2 times of 1 plus y square. Then we have 1 over x. Then plus 2 times of 2y dy dx multiplied by ln x. Okay, so we have this, and we are supposed to find the nature of the we are supposed to find the nature of the stationary point, right? So we are talking about when x is equal to 1. What is the, when it is at this point, okay, when x is equal to 1, y is equal to this, dy dx is equal to 0, what is the value of d square y dx square? So at a stationary point, it is going to be at the point 0, sorry, this point here, it's not 0, x is equal to 1. The stationary point, which is at the point 1 and negative 1.4647. Okay, at this stationary point, let me see. Oh, okay, there's something that I think I should do a bit of correction, because in part 2, we are supposed to find the coordinates of the stationary point. This is actually correct. Okay, the y coordinate is this, but because my answer should be in 3 significant figures, so I am going to go for negative 1.4, negative 1. Oh, okay, negative 1. Did I get this correct? Negative 1. Okay, this is incorrect. Let me just correct this, okay? This is negative 1.14647, my correction. So my answer here to 3 significant figures should be negative 1.15. Okay, so this is my answer, which means that at this point, I need to add in a 1 here. At this point, when x is equal to 1, y is negative 1.14647. This is a stationary point. Let's try to find the value of d square y dx square. So at this point, I know dy dx is equal to 0. X is equal to this, y is equal to this. Subbing all this information into this equation here, we have a 2 plus y, which is this negative 1.14647 square, then multiply by d square y dx square. Dy dx is 0, so this will disappear. It's going to be equal to 2 times of 1 plus y. Y is this. So negative 1.4641. I keep missing this one. So anyway, I have this square. Then x is equal to 1, so we have this. And this is going to be equal to 0 because dy dx is equal to 0. So this will help me to find d square y dx square. So at this particular point, d square y dx square is going to be equal to 1.3966. And this is bigger than 0. Therefore, the point 1, this point here, 1 and negative 1.15 is when d square y dx square is bigger than 0. This implies that this is a minimum point, right? This is minimum point. Okay. And the last part, state the equation of the normal to the curve that is parallel to the y-axis. State the equation of the normal to the curve that is parallel to the y-axis. What is going to happen when the normal is parallel to the y-axis? Let's do a quick sketch of it. When the normal is parallel to the y-axis. When the normal is parallel to the y-axis, then it should look something that is like this, right? Which means that the curve must look something that is like this. When the normal is parallel to the y-axis, that means the tangent, which is going to be perpendicular to the normal, must be one where dy dx is parallel to the x-axis, dy dx is equal to 0. And when will dy dx is equal to 0? We have already calculated dy dx is equal to 0 when x is equal to 1, when y is equal to negative 1.14, blah, 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 which means that at this particular point, we have this coordinate that is here. So at this particular point, it is going to be at the point 1 and negative 1.14647. And this is a vertical line, and we are supposed to quote the equation of this normal, right? So for this normal, which is going to be passing through the point 1 and negative 1.14647, this must be 1. So this gives us the answer for the last part, part 4. Part 4, let me just write it down here. So for part 4, my answer, just based on my observation, is this vertical line x is equal to 1. Okay, let's move on to question number 8. So for question number 8, part 1, we are supposed to make use of an identity to show another expression. So we have this. We have a 4 cosine cube 3 to the power of rx divided by negative 3 to the power of r. And according to what the question says, the numerator here is going to be, we are going to be making use of this. Okay, so by making use of this, the numerator is going to be equal to 3 cosine of theta. I'm going to replace theta by this 3rx. Then after that, plus cosine of 3 times of this, 3 times of 3rx, 3 to the power of rx. Then this is going to be divided by negative 3 to the power of r. We can re-express this definitely because our objective is to try to get this. So we already have a cosine 3 to the power of rx, which is here, and we need a cosine 3 to the power of r plus 1x. So for this, I'm going to re-express this cosine 3 to the power of rx plus cosine this. If I were to combine 3 to the power of 1 and 3 to the power of r, we'll get a 3 to the power of r plus 1 x divided by negative 3 to the power of r. This is still not what the question wants. The question wants a 3 outside here. So I'm going to do a factorization, okay? So I'm going to factorize out 3, which will then lead me to a cosine of, if I were to factorize out 3 from here. So it will leave me with a cosine of 3 to the power of rx, then plus 1 over 3. Cosine to the power of cosine of 3 to the power of r plus 1x, then divided by negative 3 to the power of r. Okay, then according to what the question says, this has to be broken into 2 parts. So I'm going to do that. So it's going to be 3 of this divided by this gives me a cosine 3 to the power of rx divided by negative 3 to the power of r. This is fine because we are already getting the first expression within the bracket here. For the second one, it's going to be plus cosine 3 to the power of r plus 1x divided by 3 times of negative 3 to the power of r. Is this what the question wants? Not yet, because I shouldn't be having that 3 below. In fact, this is going to be negative 3 to the power of r plus 1. So what I'm going to do is I'm going to factorize out negative 1 from here. So this is going to be 3. We have a cosine 3 to the power of rx divided by negative 3 to the power of r. Factorizing out negative from here, this gives me a cosine of 3 to the power of r plus 1x over negative 3. Okay, since we factorize out negative 3 from here. So negative 3 to the power of r, and this will help me to show what the question wants me to show already. So we have this 3 to the power of rx over negative 3 to the power of r minus away cosine 3 to the power of r plus 1x over negative 3 to the power of r plus 1. So this is what the question wants us to show. Let me write it down here. Assuming that we have shown this, so let me just write down the shown expression here. This is, according to the question, according to what we have just shown, it is going to be 3 times of cosine of 3 to the power of rx over negative 3 to the power of r minus cosine 3 to the power of r plus 1x over negative 3 to the power of r plus 1. So based on this that we have here, we are going to hence try to show another one. It is a series which is expressed in a sigma notation. And let me write it down. Okay, very likely we are going to be trying out the method of difference. Okay, so part 2, we're going to try to evaluate or show this r starting from 1. We're going to start from 1 all the way until n of cosine cube 3 to the power of rx divided by negative 3 to the power of r. So it looks like this, but it is lacking a 4. I'm going to try to generate a 4 by dividing a 4 outside so that I can have a 4 here. So we have a 4 to the power of 3, 3 to the power of rx divided by negative 3 to the power of r. And this looks exactly like this, which means that I can replace this with this. So replacing this with a 3, which I'm going to take it off the sigma notation, gives me a 3 over 4. Summation r is equal to 1 all the way to n of this thing that is in the bracket here, cosine of 3 to the power of rx over negative 3 to the power of r minus cosine 3 to the power of r plus 1x divided by negative 3 to the power of r plus 1. And guess what? We have already talked about it just now. We will most likely try out by making use of the method of difference. So since this minus this, so let's try to present this according to what we have learned through the method of difference. So I'm going to expand this by letting r be equal to 1. Letting r be equal to 1, we have a cosine 3 to the power of 1 x divided by minus 3 to the power of 1. Then this is going to be cosine 3 to the power of 2x divided by negative 3 to the power of 2. Then letting r be equal to 2, we have a cosine 3 to the power of 2x over negative 3 to the power of 2, which is the same as this. Then minus away cosine, letting r be equal to 2. This is going to be 3 to the power of 3x over negative 3 to the power of 3. Let me write down one more row by letting r be equal to 3. By letting r be equal to 3. So this is going to be 3 to the power of 3x over negative 3 to the power of 3 minus away, this is going to be cosine 3 to the power of 4x over negative 3 to the power of 4. So we are seeing a pattern of cancellation that is happening here, which is this, right? This and this, they can be physically cancelled. I can then imagine that for the rest, they will all be cancelled. I'm going to do a verification. Okay, although the rest is most likely going to be cancelled, I'm going to do a verification by writing down the last two rows. The second last row, that will be when r is equal to n minus 1. It will be cosine of 3 to the power of n minus 1 x over negative 3 to the power of n minus 1 minus cosine 3 to the power of n x, r is equal to n minus 1. Negative 3 to the power of n minus 1 plus 1 is going to be to the power of n. And the final row will be when r is equal to n. That is going to be cosine 3 to the power of n x over negative 3 to the power of n and minus cosine 3 to the power of n plus 1 x. And this is going to be divided by minus 3 to the power of n plus 1. So we are seeing this being cancelled in the same pattern, and we know that by our deduction, by our pattern recognition, we can see that in between will all disappear, which means I'm going to be left with just this and this. So it is going to be equal to 3 over 4 of, now we have a cosine 3x. Cosine 3x over 3. Then this is going to be minus, we have a cosine of 3 to the power of n plus 1 x over negative 3 to the power of n plus 1. Simplifying this, multiplying this in, because the expression, according to what the expression according to the expression that we are trying to show, we are definitely going to be multiplying the this 3 over 4 in. So multiplying this in, also there's a negative here from here. Okay, I've missed out this negative. So multiplying this in, we have a negative 1 over 4 cosine of 3x, which is going to be this expression over here. It is good. Let's see whether we are going to be getting this expression, which we will, because this times this gives me a negative 3 over 4 and cosine of 3 to the power of n plus 1 x over negative 3 to the power of n plus 1. Okay, so this is what the question wants us to show. Let me write down my answer here for part 2. So according to what we are supposed to show, this is equal to negative 1 over 4 cosine of 3x minus 3 over 4. Then we have a cosine of 3 to the power of n plus 1 x over negative 3 to the power of n plus 1. Okay, let me erase this. Okay, part 3 is interesting. We have this squeeze theorem, and we are given that squeeze theorem states that if cosine of 3 to the power of n plus 1 x divided by negative 3 to the power of n plus 1, basically it is this expression here. It states that this expression, if it is going to be between two other expressions in terms of p and fn, q and fn, is such that if one of the P over Fn and the Q over Fn, when n tends to infinity is equal to 0, then we can conclude that this in-between term will also be equal to 0. It's sort of like both sides become 0, so you squeeze the thing that is in the middle to make it into 0, so when n tends to infinity. And by considering the minimum and the maximum values of the cosine function, using this squeeze theorem, we want to explain why when I try to sum this to infinity, this entire expression is going to be left with this, right? When n tends to infinity, this is not going to be affected by n. This is going to be affected by n. We are going to show that when n tends to infinity, this becomes 0, so this will just tend to this. That's what the question says. Okay, so our objective here is to try show that limit when n tends to infinity of cosine 3 to the power of n plus 1 x over negative 3 to the power of n plus 1 is equal to 0 by making use of this squeeze theorem. So the question gives us a hint, which is in part 3, we are supposed to make use of the minimum and the maximum of the cosine function. I mean, obviously, this is the cosine function. And we know that for all cosine function, cosine of 3 to the power of n plus 1x, or cosine of anything, it is always going to be between minus 1 and 1. I mean, we can try to recall the graph, right? From our secondary school, it is always going to be between minus 1 and 1. Which means that if it were to be this, what I can try do is to just divide this by negative 3 to the power of n plus 1. Okay, this is what I mean, but we have to do a bit of analysis. Okay, but in general, the idea is to try to take this cosine of 3 to the power of n plus 1 x divided by negative 3 to the power of n plus 1 throughout the inequality. So it will be minus 1 over negative 3 to the power of n plus 1, then 1 over negative 3 to the power of n plus 1. This is like, you know, what we hope to do, but there is a flaw to this. Okay, if I were to just simply divide it by negative 3 to the power of n plus 1. What is that flaw that we are experiencing here? The flaw is the fact that we are not looking at a positive number to the power. If it is a positive number, for example, 3 to the power, 3 to the power of x will always be a positive number. If it is a positive number to the power, okay, of a variable, it is always going to be positive. So there's no problem dividing something that is always positive across an inequality, because we know that the inequality sign would not need to swap. But the problem comes when it is a negative number. When it is a negative number to the power, it really depends on the power. If the power happen to be equal to an even number, for example, negative 3 to the power of 4, it is going to be bigger than 0, to the power of 2, to the power of 4, to the power of 6. But if I have a negative 3 to the power of 3, an odd number, it is going to be negative something, so it's going to be less than 0. So it really depends, right? It really depends on what is the value of n, or rather what is the value of n plus 1. We know n is an integer value, but what is the, whether n plus 1 is odd or even is actually going to cause the entire expression here, negative 3 to the power n plus 1, to be either positive or negative, according to what we discussed. So I guess if we were to do this, we need to do an analysis. The analysis is for two cases. One is when n plus 1 is even. The other one is when n plus 1 is odd. It cannot be equal to 0, so we're talking about just even, odd. So we're going to look at these two cases, and let's try to do a bit of analysis based on these two cases, okay? So when n plus 1 is even, let's see. When n plus 1 is even, then negative 3 to the power of n plus 1, which I can also rewrite it as negative 1 to the power of n plus 1, then it will be 3 to the power of n plus 1. Okay, I'm just simply breaking up negative 3 into negative 1 times 3. So it will be negative 1 to the power n plus 1, 3 to the power n plus 1. And if n plus 1 is even, that means this to the power of an even, negative to the power of even is going to be positive. So I'm going to be left with a 3 to the power of n plus 1, which is definitely easier for us to manage because like what we have mentioned, 3 is a positive number. So we are going to be seeing this as just simply a positive number. Okay. Then when n plus 1 is odd, That means we will be looking at, for example, negative 3 to the power of n plus 1 is going to be negative 1 to the power of n plus 1, then 3 to the power of n plus 1. And negative 1 to the power of n plus 1 when n plus 1 is odd is going to be negative. So this is going to be negative 3 to the power of n plus 1. So we are having these two scenarios. One is when n is even, the other one is when n is odd. So when n is even, let's continue from here, okay? So when n is even, that means cosine 3 to the power of n plus 1x when it is being divided by this 3 to the power of n plus 1. The inequality sign will not need to swap, so it's going to be negative 1 over 3 to the power of n plus 1. Where the inequality sign remains the same, then it will be 1 over 3 to the power of n plus 1. So this is what we have gotten. And when n is odd, okay, let's see. When n is odd, so this, we have a cosine 3n plus 1x is going to be compared to minus 1 and 1. And when we are dividing it by negative 3 to the power of n plus 1, when n plus 1 is odd, it is like dividing by negative 3 to the power of n plus 1. So when I divide everything by a negative number, 3n plus 1, this is negative 3n plus 1. The inequality sign must swap. So it is going to become, inequality sign must swap. So it is going to become this. This is going to become this. So what we're going to be left with is going to be a cosine 3 to the power of n plus 1x over, this is going to be negative 3 to the power of n plus 1. This is going to be bigger or equal to negative 1 over 3, then n plus 1. This is going to be smaller or equal to 1 over 3, n plus 1. And just to make sure that I synchronize this expression to this, which is actually supposed to be synchronized to this over here. Okay, so if I were to try to synchronize it to this over here, right, I think we will probably need to multiply by a negative to this denominator here so that I can get a negative 3 here. So this I'm going to let it remain, and in fact this I'm going to just pump it into the pump it into this thing here. Okay, so we will have this as a cosine of 3 to the power of n plus 1 x divided by this negative, which is actually this is equal to this. So I'm going to just make this into this form. So negative 3 to the power of n plus 1. As for this, I'm going to let it remain. It's going to be bigger than this number. So I'm going to write this here, okay? Because this is the more usual inequality that we are using. So this, let me just write it down here. This expression is bigger than this. So this expression is going to be bigger than negative 1 over 3 to the power of n plus 1. And for this is smaller than this. So this is smaller or, sorry, this is smaller or equal to. So this is smaller or equal to 1 over 3 to the power of n plus 1. So this is okay because now this expression here is already one that talks about this. But this one over here is not exactly ready yet because this expression here is still not the same as this. Can we rewrite this to be the same as this? Yes, we can, because according to what we have just discussed, n plus 1 is even, which means that 3 to the power of n plus 1 is equal to negative 3 to the power of n plus 1. So let me just rewrite this. This tells me that cosine of 3 to the power of n plus 1x over this, which I can also rewrite it as negative 3 to the power of n plus 1. This is going to be less than or equal to 1 over 3 to the power of n plus 1. Is going to be bigger or equal to negative 1 over 3 to the power of n plus 1. And guess what? We are having two inequalities. They're actually exactly the same. So the result of our deduction is telling us that regardless of whether n plus 1 is even or whether n plus 1 is odd, we are still going to be getting exactly the same thing, which means that this is going to be the result even if n is changing. Okay, so, okay, fine, which means that I'm going to continue from here. Okay, I can continue with either of, they are going to be the same anyway. So if I were to just continue from here, comparing to what the question is saying, comparing it to this form over here, it is the p is equal to negative 1. And what is fn? Fn is going to be equal to 3 to the power of n plus 1. And from here, q is equal to 1. So now we can discuss based on this expression over here. Our discussion will be, according to what the question says, right? Well, from here, we can say that limit of, let's see, limit of this expression. Okay, we are looking at this expression here, which is limit of negative 1 over 3 to the power of n plus 1 when n tends to infinity. This is going to be equal to 0. And the limit when n tends to infinity of this other expression over here. So this other expression is over here is 1 over 3 to the power of n plus 1. We can see, right, when n tends to infinity, this entire expression should become 0. So we have this. So if this becomes 0, this also becomes 0. Therefore, by the squeeze theorem, therefore, we can say that the limit when n tends to infinity of this cosine 3 to the power of n plus 1 x over negative 3 to the power of n plus 1, the expression that is in between here, will also tend to 0 by the squeeze theorem. Let me just write down. Squeeze theorem. Okay, so we have managed to prove this. So once we have proven this, by considering the squeeze theorem, explain why this is going to be equal to this. So let me erase this and give myself a bit of space for me to write down the limit. Let me erase this part here. So based on the squeeze theorem, we have managed to conclude that this expression is equal to 0. Therefore, we can say that, okay, we are finally able to answer the question. So we can say that the sum from r is equal to 1 all the way until infinity of cosine cube 3 to the power of rx over negative 3 to the power of r. This is going to be equal to negative 1 over 4 cosine of 3x minus away 3 over 4 multiplied by 0, which is what we have proven. This is going to be equal to 0. So this is equal to negative 1 over 4 cosine of 3x. And this is what the question wants us to show, or this is what the question wants us to explain. So, okay, I'm going to write down the word explained. Okay, so it is this. Then the last one here, this last one is actually pretty okay. The last one, we are supposed to now try to evaluate this sum from r is equal to 1 all the way until infinity of cosine cube 3 to the power of r minus 1 pi divided by negative 3 to the power of r. So we need to try to see how this is going to be related to the previous part. So if this were to be related to this part over here, this should be 3 to the power of r, right? So x is probably going to be replaced by something. So this, I'm going to write it as from 1 all the way until infinity cosine 3. I'm going to rewrite this as 3 to the power of r, 3 to the power of minus 1 pi divided by negative 3 to the power of r. This is going to be sum from r is equal to 1 all the way until infinity. Cosine cube of this will be 3 to the power of r. This and this combined, we have a pi over 3 divided by negative 3 to the power of r. So what we are looking at is a situation of this when x is equal to pi over 3. This x over here is equal to pi over 3, right? So my answer here is going to be equal to negative 1 over 4 cosine of 3 times of pi over 3. So this is going to be equal to negative 1 over 4 cosine of pi. Cosine of pi is equal to negative 1. So my final answer here is going to be negative 1 over 4 multiplied by negative 1 is equal to 1 over 4. Okay, we're going to move on.